Verstanden. Ui. Let's there it's one. Verstanden. You see the Aufzeichnen. Yes, sir. Yeah. Hey. เขาสอนเหรอ Okay. Yes, this one here now. What's that this about? Yes, and or this. What's das ich mal verstanden? Okay. Test 1, 2, 3. Okay. This one, right. Use that. Yeah. More. This one. Mới tay. Question. Listen. Wait. No. Check out this one. Okay. In. Yeah. Stream. No. This one. 604 is it? Copy. Oh. Yes, Oscar. Okay. In Control A, Control V. Stream starten. Okay. ยังไม่ขึ้น Key in. There's nothing wrong with it. It's actually here. In stream. Okay. I'm gonna stop this. Yes. Start. Stream. Oscar. Yes. Okay. Video. Okay. White up. Schlüssel. Ui. Ui.ใหญ่เกิน อุ้ยอะไรวะอุ้ย oh my god อืม what's the problem ไว้นี่นะอะไรเนี่ยเฮ้ยทำไมเฮ้ยเอาออกก่อนเออโอเค and Einstellung stream method and how turn oh yeah this one reset copy and this one yes okay team starter right okay it works perfect okay it's nothing all right what else 6 yeah this one need to bring the is that okay test 1 2 3 okay ไปแล้วไปไม่ไปไปแล้ว test 1 2 3 okay yeah this one right so we're gonna open the microphone test 1 2 3 oh test check the audio the audio right audio use let's go let's go X test 1 2 3 okay test okay this one right I'm gonna choose the okay, audio show MV okay okay in what is nothing right 37 okay you need to observe TCL TCL32 wait TCL32 right well, what is the reason what's the reason why we don't have TCL32 Thailand so what's the problem okay okay so okay this one go to singer same connect this okay YouTube. Yes, sir. This one. Let's. I'm gonna go back. Okay. I hope that is fine. Okay. Yes. And it's time now for M604. Right? It's SCI33206, and you're gonna need to open the folder and throw away the file to this. Oh, yep. Okay. Main folder. Main folder here too. It's 4, 3 or something. And yes, 3,000. That's 28,000. Okay. Oh. Okay, and we're gonna throw away this one, right, to add up. It's in add up to nuclear physics iPad. Okay, iPad. That time. My iPad. Saving session assets and KR. Yes, strategy. Good note. Close this one. And whether anyone wanna join? No one. And this one, hot here. Chapter 7. This one. Okay, we're gonna say it's M604 28.01.2022. Right. Okay. It's right there. 7,604. Where is that? Yeah, 28. Where? ทำไมไม่มี Today's 28. Here. Okay. Good morning, everybody. Welcome you to SCI 33206. Right. It's a session for only M605. Right. This is the TCL. Safari. YouTube. Okay, just that the story. I'm not sure whether you're alive at class already or not. มากันแล้วหรือยังครับผมยังไม่เห็นนะ Okay, let me open this and this, right? Oh, yeah, leave it here, right? Safari. And what else? This one, Firefox. Okay, YouTube. Why YouTube? YouTube. No, we go to this account. This account. This account. Which account? This one too. We go to this account. This one. Go to this account. My channel. This one. And switch account to this one. Alright, มีใครเข้ามานะครับ widget your channel. Okay, this is the obvious right. Your channel. Oh no, it's the wrong one. Like this 3 stream. Okay, this is zoom. Small, make it small. Obvious. Okay, would be better. But to observe, you have to reduce. Also reduce the size. Too much. Reduce size. Too much. โอเคคำวัดมาแล้วนะผมเพิ่งเห็นนะครับโอเคOkay. Yes. Good morning, everybody. Welcome you to SCI33206, and it's the time for M604. Right? We alive at the story of no beyond that. Check กันผลมาแล้วนะครับ nuclear reaction, right? Okay, we have finished the carbon dating, right? And we will start our Yes, the nuclear reaction, which yes, what we have seen before is that we have seen the spontaneous or the nature, the composition or disintegration of the big nucleus, right? And for the human-made nuclear reaction, we could see the first case in 1919. Okay, it's the Rutherford has made the first bombardments. Yes, and you have seen the decay of alpha particle, beta particle, and sometimes it followed by the gamma emission, right? And now we will consider the human-made, the case when a human has tried to decompose the nucleus. Okay, the human tried to decompose the nucleus in 1919. Okay, it's Rutherford who tried to see whether anything new with the composition of the nucleus. Okay, and the element that he considered is helium-42. Okay, which is actually the alpha particle. Okay, and yes, the next one is that he just accelerates the alpha particle, helium-42 nucleus, to hit the nitrogen-14 7, which is what you may have seen before. It's quite close to each other. And now the alpha particle with high energy will hit the nucleus of the nitrogen-14. Okay, and the result turns out to be oxygen, okay, which has 8 proton, right? And the number of nucleon is 17. Okay, that's the case for his experiments. Okay, and the remaining thing, the one more particle is the proton. Okay, which is actually the nucleus of the hydrogen, right? That's the nucleus of the hydrogen. Okay, and we're gonna see what the human has developed to this situation. Okay. Okay. This process is known as nuclear reaction, and one of the things is we will consider first the realistic process that also take place by human in 1932, right after the experiment by Rutherford, and in England, Robert Chadwick accelerated the alpha particle. Okay, apart from Rutherford, okay, many people try to accelerate the alpha particle to hit any nucleus so that he could get something new. And one of the things is beryllium 94. Okay, and yes, Robert Chadwick has accelerated the ไม่รู้ว่าใช้สิทธิ์เขาจะเข้าหรือเปล่าไม่มีใครเข้านะครับ Okay, yeah, Robert Chadwick bombarded beryllium by using the high energy alpha particle. And after that, he got carbon 12 in one more particle. And for us here, we need to determine what is the element X or the nucleus X พิสุทธิ์มาที่ OBS 1ครับก็คนอื่นส่วนใหญ่จะอยู่ที่ Steam Lab ครับใช่ไหมที่ Steam Lab กันโอเคyes the alpha particle is accelerated to hit the barium and we need to determine X. The way to determine the element X is we have to use the reservation of particle, okay, the particle reservation in terms of nucleons, okay, above here, and in terms of proton, okay, lying below the number in the lower left subscript, and the number of nucleon is the lower left superscript, right? Okay, yes, in order to balance this equation, the number of nucleons at the input side should be the same as the number of nucleon at the output side. Okay, that's the basic thing we have to know, right? Okay, the next thing is that we consider 4 plus 9, right? 4 plus 9 and 12 plus 8. So this is 13. So A should be number 1, right? Number 1. And 2 plus 4 will be 6 plus Z, right? And we get Z equal to 0. And it turns out that we have one nucleon, and this one is not proton because number of proton is 0. So this particle is actually neutron, okay? And this is the situation when human discovered the neutron. Okay, if the initial particles A and B interact to produce the final particle C and D according to this equation. So the input is A and B. It's called sometimes reactants, okay, and the output is C plus D. So what we get is the difference between the mass at the input side, which is mass. This is the capital M represent the mass in the SI system, okay, the small m represent the mass in, I don't know what. Okay. Okay, it would be better. Okay, the mass in the small m will represent the mass in atomic mass units, and yeah, the mass at the input side, which is mass A, okay, the first reactant, and mass B, the mass of the second reactant. And we get the output of the resulting particle C and D, right? We deduce it by mass of the output for both particles, okay, deduced, subtracted by the mass of those two things. And this is the mass difference, or the mass accelerator. It depends on the situation, and we multiply it with C squared, right? This is the typical formula for the Albert-Einstein relation. And if you don't want to use the conventional expression, you may express it in small m, and that will be in atomic mass unit, and C squared will turns out to be 931.5 mega electron volt per atomic mass unit, right? And that will be more convenient for us in the study of nucleus, right? Okay. When Q is positive, okay, it means the mass at the left-hand side is greater than the mass on the right-hand side of the output. It means that the total mass decrease, okay, the mass at the output is less than the mass of the input, okay, because it's positive. And total kinetic energy of C and D will be greater than the kinetic energy of the input side. So you have a certain value of the speed for both A and B, but after the disintegration, after the nuclear reaction, you get something which is have more speed or have more that has more velocity or more kinetic energy actually. Yes, that's the case you could observe when mass excess is positive, or when the energy Q is positive. Q is actually E, okay, from the Albert-Einstein equation. This equation comes from E mc squared, right? But m is the mass difference, okay, mass difference between the input and the output, okay, reactant and the outcome, okay. And if the mass is negative, it means if the output has more mass than if the output has more mass than the input, so this one is greater than, okay, these two terms are greater than the first two terms, so Q becomes negative, right? It means the mass increases, okay, it means the mass increases. But usually the process will be the energy would be positive because it could happen, right? It could be either positive or negative, but for the big nucleus, usually Q will be positive because the big nucleus will be decomposed into smaller nucleus, and that those smaller nuclei will have more binding energy per nucleon, and they will have less mass because the mass is used to tighten the nucleon to stay together in the nuclei. Okay, for the negative Q, the total kinetic energy will decrease because some energy is used to some energy is transformed into binding energy for this one. So I don't know. Some energy is used to increase the mass of this one, so the mass become greater than before. Okay, so the energy will be negative because the mass difference is negative. Okay, and once the energy is used to increase the mass, they will have less energy. The velocity will be also smaller. Okay, the velocity will be smaller, and yeah. Yes. Next one, we go to the name, right? When Q is positive, this process is known as exergic. Okay, exergic. It's the term in physics. Okay, it's the word in physics. And in chemistry, they are gonna call, because chemistry will pay attention to thermodynamic, right? Yeah, they will use some word in thermodynamic, and it's called exothermic reaction in chemistry society. For the negative Q process, we have endoergic reaction. Okay, we call it in physics endoergic. Okay, down. Okay, down means negative, so the mass become greater and the energy is less than before, right? Down, the energy goes down. So it's known as endoergic reaction in physics. And for chemistry, they say endothermic. Okay, the thermal energy is less than before, so down again, right? Now let's consider the first example about the nuclear reaction energy calculation. When lithium is bombarded, now it's again bombardment, right? Where is that? It's 90, right? We're gonna see 90. Okay, here. The first nuclear reaction is in 1919 by Rutherford. It's the bombardment of the nitrogen 14 by helium 4. 42. Okay. And in 1932, Robert Sedgwick bombarded beryllium 94 by, again, the alpha particle. But in this process, they try to bombard lithium 73, okay, not hydrogen 14-7, not beryllium 94, it's lithium 73. They accelerate, what is that? The nucleus of the hydrogen, right? It's proton, right? It's proton, and I don't understand why. Okay, it's proton, and yes, it's proton, and they accelerate the proton to hit the nucleus of lithium 73, and they want to know what is the reaction energy Q. Okay, reaction energy Q is could be found from this expression, right? So we will start calculation of this one, right? Okay, this is the left-hand side, the input side, and this is the output side, right? So the outcome will be two particles, two copies of the alpha particle, okay, helium-42. So it's not difficult at all, right? So we're gonna compute it by using a conventional Q and the mass of hydrogen plus the mass of lithium, right, 73, minus mass of helium-42, right, minus again mass of helium-42, and you have to multiply by 931.5. The unit for that will be mega electron volt per atomic mass unit. Okay, and that's closing parenthesis. And then you have to go to the table of the atomic mass for these particle at the beginning of this chapter, right? What do we have? We need to substitute the value mass of proton, right? Mass of proton over the nucleus of nucleon. Please use the hydrogen nucleus value, not the mass of the proton. Okay, it's going to be this one. Okay, 1.007825 atomic mass unit. Okay, that's the value for the mass of hydrogen 11, right? And plus, sometimes it's called protium. Okay, protium. Mass of lithium 73. Mass of lithium 73. We have lithium 63 and lithium 73. Okay, this value, okay, 701. Okay, 701 6005, and atomic mass unit, that's the unit for. Okay. And here, because we have two terms of helium-42, right, we're gonna say minus 2 and times the mass of helium-42, whereas helium-42, helium has two isotopes in this table. It's they are helium-32 and helium-42. This is the light version of the helium, but what we need is the alpha particle, right, which is helium-42. We're going to use this value for 4002603. Okay, leave it for 4002603, and the unit is atomic mass unit, closing parenthesis, and we close the big parenthesis again because we have to multiply with 931.5 mega electron volt per unit. Okay, ที่ 9:10 นะครับ9:10 นาฬิกาเราจะหยุดนะครับเพราะว่าคาบเดียวนะครับก็เข้ามาแป๊บเดียวนะ Okay, and after that you just leave it in the calculator, right? You're gonna get the answer like 17.35 mega electron volt. Okay, and that's it. for this process. Okay. Yeah. You know that we start from the typical formula from the Albert-Einstein relation, right? But we don't use this formula exactly, right? We use the mega electron volt version. Okay, this is the SI version. Okay, it's meter per second. You 3 times 10 to 8 square, blah blah blah, right? And the mass here you need to substitute the mass here should be substituted in kilogram, right? But this one you just look for look for them from the table in terms of atomic mass unit. Okay, and that's more appropriate. Okay, now we go to the next section. After the bombardment in 84, the total kinetic energy of the two separating alpha particles will be 17.35 greater than the initial total kinetic energy of the proton and the lithium nucleus. So it means you have greater kinetic energy, but it's not the value of the kinetic energy of the output, okay, of proton and lithium of alpha particles. No, it's not the case. It means the kinetic energy of the output will be greater than the kinetic energy at the input side by 17.35. Okay, that's the meaning. Okay, now let's consider the next process. We consider the reaction energy, which is made by Rutherford, right? Rutherford is showing here. Okay, Rutherford accelerates the alpha particle, right? Helium-42 to hit the what is that? The alpha particle. He want to hit the nitrogen 14, right? And it turns out to be oxygen 17.8 and proton. So let's compute this one, right? It's not difficult, right? The way to do that is you write down the mass of Q will be mass of helium-42, right? And plus mass of nitrogen 14.7 minus mass of oxygen 17.4 and minus mass of proton 1.1. Okay, and you multiply it with 931.5 mega electron volt per atomic mass unit. Okay, and you substitute mass of helium-42 because you accelerate helium-42 from this table at the beginning. Okay, here. Yes, we look for this again. Helium-42 is this one, right? 4002603, 4002603 atomic mass unit, and plus the mass of nitrogen 14. Nitrogen has two isotopes, nitrogen 14.7, nitrogen 15.7. We're going to use this value 14.003. Okay, 14.003074. Yes, that's the second mass, and after that we have the negative value of oxygen 17. Okay, oxygen has several isotopes. It's oxygen 16.8, right? This is oxygen 17.8. Oh, what's the problem? Okay, the next one is nitrogen 17, right? So we will look for the value for that oxygen 17. Oxygen 17 will be oxygen 17, right? This one. 16.99 is not 17, it's 16.99132 atomic mass units, right? And the mass of the proton is this one, right? Minus 1.007825, and units, and we close it, and is 931.5 mega electron volt per atomic mass unit, and closing parenthesis, and it now turned to be the result. And after you make the multiplication, you get 92. Okay, 92. Oh no. Where's that? It's over here. Also, it's negative 1. Okay, negative 1. Negative 1.192 mega electron volt per atomic mass unit. Kr. Oh no. It's only the energy unit, right? Okay. Yes, you could see that it can happen that the energy turns to be a negative value, and yeah, you may see that what is the meaning to this? It means in this process, in this process, okay, the Rutherford experiment, the oxygen 17 and the proton would have less kinetic energy than the input side, because you accelerate a lot. Okay, accelerates the alpha particle with high speed, and it hits the nitrogen 14, and after that the mass turns to be the mass of these two particles turns to be greater than the summation of the mass of at the input side. So the energy is used to increase the mass at the output side, and once the mass increases, the energy decreases, and yeah, both particles will have less velocity, have less kinetic energy, and that's the meaning of the negative value. All right. Now we move to the next one. The amount of 1.9192 mega electron volt is the energy absorbed in the reaction. And Rutherford reaction will take place if the total initial kinetic energy is at least 1.192. This is the smallest value of the kinetic energy you could have. Okay. If you increase or accelerate the alpha particle with less than this kinetic energy, the Rutherford process will not take place, will not occur anymore at all. Okay, that's the meaning of this one. Okay, the story about physics is that we have to calculate the energy. Okay, and okay, endothermic, right? Endo down, right? The mass increase and the energy is negative. Endothermic reaction will not occur unless the incoming particle has at least enough kinetic energy to overcome the energy deficit. Okay, because there is energy that tied to by the nucleus, and you need to have kinetic energy greater than this energy so that you can decompose this nucleus or nuclei. Okay, all right. Now we move to the nuclear fission, the next topic, but the time is over right now, right? It's 9:10. It's better to start this one next time. This is 28.01.2020. Oh, 2022, right? The homework for you will be carbon dating, right? Carbon dating and the nuclear reaction energy, right? Nuclear นะครับการบ้านนะครับreaction energy นะครับเพื่อว่าคุณจะได้มีจำนวนการบ้านเท่ากับ65ครับโอเควันนี้ก็คงต้องจบไว้เพียงเท่านี้นะครับวันนี้จบเพียงเท่านี้การบ้านเดี๋ยว create ที่ Google Classroom นะครับได้แก่2เรื่องก็คือ carbon dating นะครับแล้วก็ nuclear reaction energy นะครับก็คือที่พาคำนวณตะกี้นะครับ Q เท่ากับอะไรเงี้ยคุณไปหาโปรเซสมาที่เขาเร่งอนุภาคกันไปชนนิวเคลียสนะครับแล้วแตกออกมาเป็นต่างๆนิวเคลียสที่ทำโดยมนุษย์นะครับโอเค man made nuclear reaction that's the thing you need to find okay if you don't like it you may look for any problem regarding or related to carbon dating okay to determine the age of an organism by using half-life and so on ครับวันนี้ก็คงต้องจบไว้เพียงเท่านี้เพราะว่ามีคาบเดียวครับ see you oh anyone want to join โอ้ใช้สิทธิ์ใช้สิทธิ์เพิ่งเห็นนะครับโอเคใช้สิทธิ์พิมพ์ชื่อมาแล้วกันนะโอเคใช้สิทธิ์เข้ามาหมดเวลาแล้วก็604นะครับเราพบกันแป๊บเดียวนะมันไม่ได้อาจารย์ครับยังไม่รับผมว่าซูมเพิ่งเห็นครับขออภัยด้วยเพิ่งพิมพ์มาที่ไลน์นะโอเคพิมพ์มาตอน849นะครับโอเคขออภัยด้วยครับใช้สิทธิ์พิมพ์ชื่อมายังโอเคพิมพ์มาแล้วนะครับเป็นหลักฐานนะโอเคพบกันวันพุธหน้าเนาะวันพุธหน้าก็บ๊ายบายครับขอให้เรียนวิชาคณิตศาสตร์ของอาจารย์ณัฐพงศ์อย่างสนุกสนุกสนานนะครับโอเคบ๊ายบายครับสวัสดีครับ what else map to yeah go live of SteamNet right ไปที่ SteamNet okay SteamNet please yes โอเคพวินเอกวัตรเนาะอ่านภาษาไทยเอกวัตรมีประมาณนี้แล้วก็ซูมมีไหมเนี่ย obvious number one right obvious number one obvious number one and Google Classroom no Google Chrome here yes no okay and now just go to YouTube Studio YouTube go live YouTube stop I just 3 people like this no go live to Zoom to YouTube channel Zoom to YouTube channel Zoom to So to YouTube channel this one. It's not made. Yes, it's not entertainment. It's education. Education. Oh yeah. Education. It's education. Oh no. What else? Yes, education, and gotta have some description to it. And just Control A. To save it like that. Stop. No run here. Cancel. I think there. See this one. Go to city card to this one. On me next in YouTube Studio to go live in manage. That's it. And this one. Yeah. Okay. That's the got what couldn't find something. Got what now? Got what? Soup. Okay. We stop this thing. 4. Let's say got what top win. Top win piece of it. Banyak ถึง banyak จบแล้วก็ cancel file. Okay. Send a form. Oh, already. 604. This one, right? Okay. Oh, wait. Okay. These, okay. 2 things. 2. Okay, we now finish the meeting, right?